bond polarity, if we look at the HF molecule, we see that the electron cloud is not symmetric. The electron cloud is asymmetric. So let's do this. Electron cloud is asymmetric. That means it's polarized towards fluorine here because fluorine is more electronegative than hydrogen. And so we got more negative charge density around fluorine. There are different ways we can represent it. We could say delta minus, there's a partial negative charge on fluorine. It hasn't completely stripped it away, delta plus. Or we can use bond dipoles like this, bond dipole. In HI, there's a much smaller difference in electronegativity. And so in HI, it's much more symmetric. And so this generates very small delta minuses and delta pluses and very small bond dipoles compared to here. Now, if you're a base, like a hydroxide ion, which one would you be more attracted to? The HF. If you're a base, you're negatively charged, you're going to be more attracted to this hydrogen than this hydrogen over here, because this one has a much higher positive charge. But even though you're more attracted to this hydrogen is a lot harder to pull off the molecule than this hydrogen. And so you might be less attracted to this hydrogen, but since this hydrogen is much easier to pull off, this hydrogen comes off. It turns out HI is a stronger acid. But typically, bond polarity, we'd expect the more polar one to be more reactive. But in this case, the more polar one, yes, it is more reactive, but no, it isn't more reactive because the bond is too strong, or stronger. Up to an extent. And so as far as bond polarity goes, this is the ranking we would have. We'd have that the HF should be the highest in terms of bond polarity. And HI should be the lowest bond polarity. And so this is for bond polarity. Therefore, we would expect HF based on bond polarity to be the strongest acid. But it turns out bond polarity is a secondary effect. And so as far as acid strength goes, bond polarity predicts HF should be the strongest, HI should be the weakest. But experimental observations show the opposite to be true. By observation, HF is the weakest, and HI the strongest. And so what this means is that the most important factor is bond energy. And so polarity, we can map out in Spartan. The way Spartan does it is it uses a color coding system. The color coding system is going to map this fluorine atom as having more negative charge density than this iodine atom. And do you guys remember the electrostatic maps in Chem 1A? They had two colors, actually three. They had red, blue, and green. Red is negative or red is positive? Negative? Yeah. Red is negative. That always confuses me because, you know, in batteries, we usually have red as the positive. But it turns out red is negative. And so this atom's going to appear more red, obviously. And then blue, actually I probably shouldn't do it on this, because I used blue already. But if we were to do this quantum mechanically, what we get is we get a map, electron density map. This would be an electrostatic map. For HF, that looks like this. The hydrogen is going to be red. The fluorine will be blue. And somewhere in between, we'll see some green. It's more neutral. Okay, when we look at HI, then it's just a more green, less red and blue. And so it's not going to be as polar. And so in quantum mechanics, using a program like Spartan, we'll generate electrostatic maps like this. But the nice thing about Spartan is this. Rather than saying delta minus, and this delta minus is smaller, what we can do is we can right-click on an atom in Spartan. When we right-click on an atom and select properties, it'll tell us the charge. You know, so is the negative charge, well, the negative charge is between 0 and -1. So is the negative charge -0.5? Is the negative charge -0.8? You know, what is the negative charge? And likewise, what is the positive charge? You know? Well, if the negative charge is 0.8 minus, then the positive charge must be plus 0.8.
Wait, did you just say that red is negative?
Oops, yeah. Red is negative. So I have it backwards. I always think red is positive. I always think red is positive because of the electrode on batteries. I always think blue for bases. Blue for bases, blue litmus, right? Bases are negatively charged. And so I always get it mixed up. I always have to remember electrostatic maps are backwards from my thinking. Red litmus, you know, red litmus is for acid. Acids turn litmus red. And so this always mixes me up. Now, what we can do is polarity becomes a factor if the bond strength is the same. And so if bond strength is about the same, you know, then polarity is the most important factor. And polarity, well, polarity is a significant factor. Then polarity is important. All right, so let's take a look at the two molecules here. We're going to look at methanol. And methanoic acid. Methanoic acid is also called formic acid. We'll just call it formic acid. The common name is much more common. Than its systematic name. Over here, methanol is much more common than wood alcohol. Wood alcohol its common name. Well, let's take a look at the two hydrogens here. You know, we have hydrogen bonded to the oxygen. This hydrogen is typically not thought of as acidic. You know, this one bonded to electronegative oxygen should be acidic. That has a lot to do with polarity. This hydrogen is not so polar. This one is highly polar. And so this one's going to attract the bases for sure. Well, this one's polar as well. And so we have an HO bond, we have an HO bond here. Are these two going to be equal in strength? So is methanol just as good of an acid as formic acid? Well, it turns out no. Methanol is so weak it's not even considered an acid. Why is that? Well, it doesn't have to do with the HO bond. The HO bond is about the same strength. It has to do with polarity, but you think about polarity, the polarity should be the same. The polarity of this oxygen, well, that's electronegativity 3.5. This oxygen, electronegativity of 3.5. And so delta En, that is the difference in electronegativity, is the same for both of these. And so it seems like both bonds are equally as polar. But that's not the case, because what happens is the next atom can impact that. Well, the next atom's carbon. This atom's carbon as well. But are these two carbons, when you look at these two carbons, do they look the same to you or quite a bit different? These two carbons are not the same. You know, carbon typically has an electronegativity of 2.5. Well, these two carbons are totally different. And there's two ways we can show that these two carbons are totally different. One way we could do that is by the inductive effect. Do you remember the inductive effect? The inductive effect is this terminal oxygen pulls electron density away from that carbon. And so the electron cloud gets pulled toward the oxygen, which means the carbon comes up short and starts to pull on the electron cloud here, resulting in a pull here. Whereas over here, oxygen pulls the electron cloud away from carbon and hydrogen. And so we call this the inductive effect here. That's one way of looking at it. Another way of looking at it is looking at the carbons. The two carbons are different. And we can see that not by formal charge. The formal charges on these two carbons are the same, but we can see that based on its oxidation state. What is the oxidation state of this carbon here? Can you eyeball it now? -3 is correct. Do we call that electron rich, electron poor, or somewhere in between? Call that fairly electron rich. The richest would be -4. It's pretty rich. What's the oxidation state on this carbon? The oxidation state on this carbon is +2. And so this carbon's electron poor relative to that carbon, which is electron rich. And so what that's going to do is it's going to impact its electronegativity, because electronegativity depends on its oxidation state. And so here, the electronegativity of carbon is 2.5. Well, that's a neutral carbon. A carbon with a -3 charge is going to have a much lower electronegativity. It really doesn't want many more electrons or electron density. It's not really going to pull it. Whereas a carbon in a +2 oxidation state is going to be more electronegative. It's going to have a higher electronegativity than 2.5. And so that's going to distort the electron cloud there. So when we look at this atom, these two atoms are different in that respect. And so we can see, well, that's going to impact the electron cloud in this linkage here versus that linkage there. Not only is that going to impact that, but, you know, this is going to be the most acidic proton, because this is going to be the most polar over here. This is going to have the biggest delta plus. This delta plus is going to be smaller here because of that. And so the bases are going to attack that. Are the bases going to be attracted to these hydrogens? No, these hydrogens are non-polar, and so they don't really attract it. And plus, the bond is kind of strong. Well, the bonds are strong for both of these. However, take a look at this hydrogen. Is this hydrogen-carbon bond the same as this hydrogen-carbon bond? Would you treat these two hydrogens equivalently? Are they going to behave the same? What do you think? No, these two hydrogens are going to behave differently. In fact, one of them is going to be more acidic than the other. Which one is more acidic? Well, the electronegativity difference here is so small. You know, it doesn't produce much charge here. So we'll see that. These are all green, pretty much. Over here, this hydrogen, however, is going to be a lot less green. It's going to be more more blue. And so, in fact, this hydrogen here is going to be quite a bit more acidic. So potentially this hydrogen could also react. And so this hydrogen for sure, but this hydrogen potentially could react as an acid. Whereas these you wouldn't expect to act as an acid. And so sometimes this happens in organic chemistry especially. You have to look at the hydrogens that are attached on the other carbons. And so they name the other carbons, the alpha carbon, the beta carbon, and the protons attached to those, or the hydrogens attached to those. And so these hydrogens and these hydrogens are different, and this is just because of how the electron cloud is distributed in the molecule. So we're going to build this. Actually, we're not going to build methanol. We're going to build a series of carboxylic acids, like formic acid. Let's take a look at another example here. Do you know how you would name this? Take a guess how you would name that. Over there. Well, it looks like acetic acid, except the chlorines have replaced the hydrogens. So this is called trichloroacetic acid. Trichloroacetic acid is a strong acid, or borderline strong acid. Some people call it strong acid. And it is a pretty strong acid. What makes it such a strong acid versus acetic acid, which is a weak acid? Well, one, you could say the inductive effect. But the inductive effect goes even further in this particular molecule because we have these electronegative chlorines, right? The other is you could just look at the difference in the carbons. So for example, here we got all this pulling of electron density, or the electron cloud, away from this carbon. And then we have this, right? And then we have this. Which way is it going to go? Which way? Figure it out. We can figure it out based on the charges. Let's take a look at the oxidation state, because this one might be more tricky. What's the oxidation state on this carbon here? The oxidation state on this carbon is plus 3. The oxidation state on this carbon, plus 3. And so both of these carbons are quite electron poor. Versus something like acetic acid. Acetic acid is a much weaker acid. is a much weaker acid because the inductive effect here with this group, carboxylic acid group here. And when we look at this carbon here, this carbon is, what's the oxidation state of this carbon? This one's the same on the right. This is +3, but this one is what? -3. So it's quite a bit different. And so what the end result is this. When we map this out in Spartan, we're going to see a much bigger positive charge here than here, making this one much more acidic. In Spartan, we can see that in two ways. We can right-click on this atom and figure out its charge, electrostatic charge, or we could look at its blue. You know, this is going to be more intensely blue over here. Okay, this will be less intensely blue, more towards the green. So that's trichloroacetic acid. All right, polarity will impact it if the bond energy is about the same, which it is for carboxylic acids. Are there other factors that impact? And there are. The next factor is the stability of the conjugate base. So we look at the charge density. Charge density. So as far as charge density goes, let's compare oxide with hydroxide. Which one's a stronger base? Which one's more stable? Which one's less stable? Well, which one's a stronger base? Well, a base attacks what? Well, a base is red. Red because of negative charge density. Which of these two would be more red? Oxide or hydroxide? And why? Oxide's going to be more red than hydroxide. Why? Even though their oxidation states are the same, the formal charges aren't. Formal charge is a net charge in this case. And so in this case here, we got 2 negative, and so this is -2 concentrated on oxygen. Whereas this oxygen, yes, it has a hydrogen attached to it, but this oxygen is a -1. So here we have a -2 charge on an oxygen atom. Here we have a -1 charge on an oxygen atom. Which one's going to be more red? The -2. It's got more negative charge. Well, this -2, which one is going to be attracted? Well, it's red. It's going to be attracted to blue. Which one is going to be more attracted to? This one. And so this is a stronger base. A stronger base because it has a higher charge density. A stronger base is less stable than a weaker base, which is more stable. Both of these are powerful bases, but in relative terms, hydroxide is more stable. Let's try another example here. This is in chapter 16. Sulfide versus oxide. Now both of those are -2. Which one's stronger? Oxide or sulfide? Which one's stronger, oxide or sulfide? Sulfide? Turns out, no, it's not sulfide is a strong base for sure, but oxide's more powerful. Why? Sometimes I ask this in Chem 1A, you know, because normally I talk about this in Chem 1A. And I ask the question, why is oxide a stronger base than sulfide? And some people will say electronegativity. Oxygen is more electronegative. But that doesn't make any sense at all. And so when I read an answer like that, because oxygen is more electronegative, then I realize that they don't understand electronegativity changes depending on the charge on oxygen. Is oxygen really electronegative? Yeah, people will say oxygen is the second most electronegative element on the periodic table. And so that means oxygen wants another electron. Oxygen is going to pull another electron to it. And hopefully it gets that. Does oxygen really want another electron? No. And so what they meant to say is oxygen is highly electronegative, but oxide is not. Electronegativity. Whereas an oxygen cation would be extremely electronegative. This really wants an electron. But this has already got an octet. Does it really want more electrons? Can oxygen go beyond an octet? No, because that extra electron is going to go in the next higher energy shell, which is going to be highly unstable. And so oxide is not more yes, it is more electronegative than sulfide, but we aren't looking at electronegativity because bases don't want electrons. Do bases want electrons? No, acids. Acids want electrons. Acids are blue. Electron density is red, right? So acids want electrons. Therefore, in organic chemistry, they call acids electrophiles. Right? Acids are electrophiles. Whereas bases are not called electrophiles because they don't want electrons, so electronegativity is not what we look at for bases. The bases are called, do you know what they're called in organic? Bases are called nucleophiles, right? A proton, what is a proton? A proton is the nucleus of the hydrogen atom. It's positively charged. And so bases want positive charge, you know? And so these red bases are looking for blue positive charge. And so which one's a better nucleophile? Which one's a better nucleophile depends, you know? Which one can seek out that positive charge better? And so here we have sulfide. Sulfide's much bigger than oxide. And when we look at the charge density, sulfide has 2 minus over a bigger volume, whereas oxide has a 2 minus charge over a smaller volume. And so which one's going to be more reactive? Oxide is going to be more reactive. Oxide's a better nucleophile. Oxide has a higher charge density, higher negative charge density. Red, you know, the deeper the red, the more basic it is, and the more it wants to attack the blue. Right? And red is nucleophile, not electrophile. People get this confused and mixed up, you know, nucleophile, electrophile stuff. You know. Ammonia, for example. Ammonia is a base. Does it really want electrons? Is it electrophile? No. It's a nucleophile. All right, let's go on here. When we think about charge density, then we talk about localization versus delocalization. Here, you know, when it's concentrated, it's localized in a smaller volume. When it's spread out, it's delocalized over a bigger volume. So the more concentrated, the more localized it is, the more powerful the base, the less stable it is. The more we can delocalize or spread out that negative charge, the less reactive it's going to be. And so what are the ways we can delocalize the negative charge? There are different ways. So for example, here, if we look at this ion, this is called methoxide ion. We have a negative charge on that oxygen. That negative charge on that oxygen is going to make it quite reactive. Just like a negative charge on formic acid will make it quite reactive. And so what we have is this is called formate ion or methane. It's called formate. Should they be about the same strength? Yeah, it looks like it, but it turns out that formate is much weaker. In fact, methoxide is considered a strong base, like hydroxide. Methoxide and hydroxide have about the same strength. And so why is methoxide a strong base but formate a much weaker base? It has to do with two things. There are two reasons why formate is it. One is delocalization by the inductive effect. Here, now we can argue. Why are these two different strength bases? And which one will be stronger? It turns out that ClO minus should be stronger. You know, we predict this one to be stronger. And we predict this one to be weaker. Why? Well, it has to do with the inductive effect. That is, some of the negative charge density here is going to be pulled towards chlorine. But over here, fluorine's more electronegative, and so it's going to pull more of the negative charge density. And so what that means is some of the negative charge is going to be pulled in, and therefore it's going to weaken the basicity of that. There. And so we can see the same thing here. When we compare methoxide what's the charge on this carbon? When we look at methoxide, the charge on that carbon is 2, 4, 6, 7, minus 3. That minus 3 charge is going to pull in electron density, or not. No, that minus 3 charge, does that want more electron density? That absolutely does not want more electron density. So what it's going to do is it's going to push that electron density out. It's already got lots of, it's already electron rich. And so that means that the negative charge here is going to be more localized on the oxygen because carbon doesn't want to take any of it. However, if I look at form 8, then this is a different story because this carbon's different. This carbon is 2. And so that means this carbon is plus 2. If this carbon's plus 2, then this is capable. This carbon would be happy to accept electron density. And so some of the electron cloud can be pulled towards that carbon, which means that the charge on this oxygen is going to go down. Whereas over here, none of the electron cloud is going to be pulled towards the carbon. In fact, it's electron rich, so here. And so in the scheme of things, this one's going to be much brighter red in terms of electrostatic mass, and this one's going to be a much less intense red. And so that's delocalization via inductive. We also have one other factor, and that is delocalization via resonance. And so this is called resonance delocalization. Well, resonance delocalization is this. Can we draw any resonance forms for methoxide? Methoxide doesn't have any resonance forms. However, formate does. And so one of the resonance forms for formate looks like this. The second resonance form for formate is going to look like this. But what we want, a more accurate depiction is it isn't bond order 2, bond order 1. More accurate structure would be the resonance hybrid. The resonance hybrid is going to look like this. Let's do it over here. Where each bond, is going to be 1.5. Bond order is 1.5. There are 2 lone pairs on each of these, and then 1 lone pair that's delocalized over both. That's going to lower the charge. The bond order went to 1.5, and the formal charge has to be distributed over 2 atoms. And so negative charge distributed over 2 atoms means each atom is going to be negative 1/2, negative 1/2. And so which one do you think has a bigger impact on delocalization of charge? The inductive effect or resonance? It turns out that this resonance delocalization is much more significant. And so this is the more important. The inductive is going to be minor because it doesn't lower the charge tremendously here, even though that's +2. In reality, both occur because this carbon is still +2. So, these are negative 1/2 by the resonance, and then that charge is going to go down a little bit because of the inductive effect. And so what this means is that formate is much more stable than methoxide. And one of the driving forces is forming stable products. All right, the last one is, last factor we got to look at is solvation / hydration of the conjugate base. Let's do a quick aside here and look at redox. One of the weird things in redox is lithium. Lithium versus potassium, let's say. If we look at the ionization energies, then lithium has a much higher ionization energy, which makes sense because lithium is a smaller atom than potassium. And so smaller atoms are harder to ionize. Bigger atoms are easier to ionize. And so which one is a better reducing agent? It turns out lithium is a better reducing agent than potassium. But the ionization energies predict the opposite. And so it's not due to ionization energies, because if it was strictly due to ionization energy, potassium would be a stronger reducing agent than lithium. Potassium, it's much easier to take the electron off. So an oxidizer comes along, it'll have a much easier time stripping the electron off of potassium than a lithium. And so it's not because of ionization energy. Maybe it's stability of the conjugate. And so let's try stability of the conjugate. Now in this case it would be the conjugate oxidizer because we're looking at the reducer. And so that would be the lithium ion versus the potassium ion. Which one should be a stronger oxidizer? The lithium ion or the potassium ion? Well, oxidizers are looking for electrons, so which one will have an easier time stripping electrons off something? The more concentrated positive charge or the less concentrated positive charge? The more concentrated, so this is a stronger oxidizer. This is a weaker oxidizer. And so that means that potassium ions are more stable. They're less reactive. So if potassium ions are more stable, less reactive, then that once again tells us that potassium should be a better reducing agent. And so both of these tell us potassium should be a better reducing agent. Stronger Ra. Why lithium wins out is because of how the solvent interacts with it. Why lithium is the best Ra has to do with solvation, hydration. Solvation and hydration are talked about in chapter 13. And what that is, okay, if I have a lithium ion here, then it's going to be surrounded by water molecules. In other words, hydrated by water molecules. When lithium becomes hydrated with water molecules, we get what's called an ion, that is lithium dipole attraction. These ion dipole attractions help stabilize the ion in solution. And we get fairly strong ion dipole attractions here because lithium is a small ion. Do you guys recall Coulomb's law? Coulomb's law is from chapter 2. Coulomb's law just says that the force of attraction or repulsion is going to depend on the magnitude of the charge on A and B. So if we're looking at the force of attraction or repulsion between A and B, we need to know the charges of each. And then we also need to know the distance between the center of the charges squared. The other thing is we can look at it in terms of charge density. This is a higher positive charge density. And so that higher positive charge density is going to be able to hold on to waters more strongly than this. This is a lower charge density. And so that interaction's weaker. And so what happens is that water helps stabilize lithium ions significantly more than potassium ions. And therefore, we form a more stable, hydrated ion. There are other, other waters on here I'm not showing. The other way of thinking about it is distance. Distance is very important. So this can get closer to the center of the charge. Over here, this is farther from the center of charge here, so the force is weaker. All right, the same thing applies with acids. When we look at the conjugate bases, small conjugate bases that are highly charged can be hydrated nicely, potentially. And so hydration might, but it's more tricky because now we're looking at things like formate or whatever else. It can get more difficult to determine, or it might be not so difficult to determine. All right, I'm going to stop here. We're going to move into the computer lab next. We don't have that much time, but we aren't going to do the Spartan today because the software